control. So the title has changed. He's going to speak about something else.
Let's move this. Okay. Yeah, good morning, everybody. I'm very happy to see so many here in the room after yesterday's banquet. As you have seen here, I changed the title a little bit. There was a last, or well, not last minute, last day decision to do so because we have a quite nice simulation of pipe flow at a reasonably high Reynolds number, which I thought could be quite nice to present here in this audience. So therefore, the two topics that I'm going to talk about today. Of course, that doesn't work. Okay. Okay. Well. So yes. Yeah. Okay. So the two parts that I would like to talk to you about today is first of all about hairpin vortices. So here you see an example of one of those, and then in the second part I would like to talk about this pipe flow simulation. And so what do I want to talk about when it comes to the hairpin vortices in the first part? So essentially, it's to some extent a historical kind of account of what happened maybe 10 years ago when we were for the first time able to actually perform simulations of spatially developing boundary layers. And at that time, there was quite some dispute between different simulations, different people looking at the data, whether or not there are hairpin vortices in the data or not, whether something is a hairpin or not. So what we tried to do during that work was essentially trying to find ways of being able to identify hairpin vortices, trying to find them in the data sets. We then also tried to look at whether some of the proposed mechanisms of hairpin vortices multiplying actually work in turbulent flows or not. And then at the end, kind of because maybe these two first points were not so easy as we thought initially, we also tried to make hairpins artificially and see to what extent they actually survive. So that's kind of the outline of the first part. So as I said, this is work, of course, that I have not done alone. There's a lot of people from KTH, including also Don. There was collaboration with Fazli Hussein and also with Oscar Flores from Madrid. And if you want to read about it, there's these two papers that we published on that topic. So if you, I will not cite that on every slide. So whenever you're interested, you can go to these papers. So as I said, kind of the background was we were able to, for the first time, simulating these spatially developing boundary layers. There were, of course, all these very nice structures that you can get in these very long domains. I guess we have now seen all these streaks and large-scale structures before. You can zoom in because it's DNS. You see all this beautiful detail. But I guess the main thing, okay, that's not as smooth as I thought it would be. But the main thing was these structures here identified with lambda 2, which, of course, seem to be reasonably regular. But the higher the Reynolds number becomes, the more irregular these structures become, and you know, it doesn't really look like very ordered hairpin vortices anymore. I guess the question was, what type of vortices these are, and to what extent they're actually building blocks of turbulence, and perhaps also what is the relevance of these vortices. So very quickly we realized that, of course, everything has to do with how we force turbulence, how turbulence actually comes into the domain. This is just a quick illustration of different ways of how you can do that. You can have a tripwire. You can have kind of bypass type of transition where you get the individual spots, and you can also go via the classical route, K-type in this case, to transition. Then, of course, very quickly after the transition, you can see these type of hairpin-like structures. And that's exactly the region where I would like to focus on in the first part. So where does this actually all come from? And I guess the first kind of conceptual description goes back to Theodorsen in 1952, where he hypothesized that vortices like this could be relevant building blocks of turbulence. Later on, this was then, of course, also discovered in experiments, which made them as kind of a thing in turbulent boundary layers. There were some criticisms regarding that experiment, that maybe the trip was a little bit too strong, so therefore these hairpin vortices may not have been real vortices at the time. I guess one of the key papers, early papers on looking at structures in boundary layers, turbulent boundary layers, was the analysis of the Spalart DNS by Robinson. And he had this kind of hierarchy of different vortices, where there were not really hairpin vortices close to the wall, it's mainly quasi-streamwise vortices and kind of arches or canes further away from the wall. Then I guess extremely important in this whole discussion is of course the work by Adrian in a series of papers, and I guess we've all seen this sketch here before, which is kind of the key description of the hairpin model for turbulent boundary layers, where you have these low momentum zones, and then you have hairpin-type shaped vortices wrapped around. One of the key aspects here was this data, or this description, came essentially from looking at two-dimensional PIV data and seeing these ramp-like shear layers, and then these kind of regions of increased swirl being aligned along these ramps, which was then called for hairpin vortex signatures, as being kind of when they cross through the PIV plane. Simulations, of course, were also at that time providing three-dimensional data. There it turned out to be much more complicated to find these structures, as we have also seen in the animation before. And it actually turned out that it seems to be much more complex structures, not these very nicely oriented hairpin vortices, as you can see in these figures here. Experiments at the same time, three-dimensional experiments. I guess it's a little bit difficult when it comes to the resolution at that time to find out exactly how structures look like with the spatial averaging, etc., going on. But there's certain aspects where you could potentially identify hairpin vortices. The main paper that kind of motivated our study, and I guess also brought back the idea of hairpin vortices into our community, was the paper by Wu and Moyne in 2009, and then a couple of follow-up papers later on, where they essentially provided this visualization, or a sequence of similar visualizations, where essentially you can kind of infer from the figure that there is these regularly structured span-wise where the head is kind of in a span-wise plane of hairpin vortices. And this was kind of really the origin of our motivation to actually go in and try to find out, are these vortices really hairpin vortices, and how important are those vortices also when you go to higher Reynolds numbers, so when you go a little bit away from just the immediate tripping location. So we in the first step, we were perhaps a little bit naive, and we thought, okay, let's just look at visualizations, let's try to find them. And we went back to the Adrian paper. We tried to identify exactly these ramp-like structures, these hairpin vortex signatures, and then look at visualizations, because we have the three-dimensional field, so we could just look at it. So we could find exactly the structure in a span-wise wall normal plane, where you have these ramps. We have these not low momentum zones, the hairpin vortex structures. And for instance, if you then look at this, we looked at many others as well. But if you, for instance, look at this structure, you can then, of course, you get very complicated spaghetti-like things. But we very quickly realized that actually the hairpin vortex structure is, of course, a cut through a vortex. That's why you also see it. But it turns out that this vortex is just a vortex that is oriented in some way that cuts through that plane. And this is just one example. It's of course very difficult to interpret it in a more statistical manner, but in the end, everything kind of looked like that. So it turned out to be very, very difficult to just base our conclusions on visualizations. So the next thing was then that we tried to do a little bit more statistical work on that, and we went back to a paper by Jeong and others, and Fazli Hussein, who did a similar analysis in channel flow in the late 90s. So the idea is to identify hairpin vortices not starting from the head, but starting from the legs. So the idea would be you would identify somewhere close to the wall, y plus lower than 100, you would try to identify streamwise vortices or quasi-streamwise vortices, which would then be the heads, the legs, and then you would do a statistical average of those, an ensemble average, and then you would see whether there is actually a head attached to the legs. And that seemed to be a very, very nice way of identifying that. So we implemented that, and we ran it also for our boundary layer data. First, we started close to the tripping, so where we actually see these hairpin vortices, also in our simulation, just coming from the way that we introduce turbulence. And then actually it turned out we averaged over, well, a reasonably small ensemble of 14 structures, which all kind of look like this. If you do this average, you get this ensemble in the end, which actually looks like that there is, something attached to the leg, as you would also expect for the method to give in a flow field that is visually clearly dominated by hairpin vortices. So that was fine, but of course nobody of us would say that this is a turbulent flow yet. So I guess much more interesting it was then to actually do the same method when you then go to higher Reynolds numbers. We did it at a sequence of Reynolds numbers, and unfortunately what came out here is essentially just this kind of sausage. There was nothing attached on the front, and this sausage, the quasi-streamwise vortex, is very similar to also the original paper by Jeong in channel flow, and there was no significant change between channels and boundaries. Perhaps also as one would expect. So there we could really not see anything, no appendage or anything on these vortices. As I was saying, this compares, this sausage in our case compares very well between channels and different Reynolds numbers. You can do statistics on it, on the rotation, inclination, and all of that. Everything matched perfectly. So the conclusion from this ensemble type of study was there seems to be also no hairpin present. Okay, so of course that was a little bit, well, frustrating or not, but that was a result which was not showing anything, maybe not what we expected based on the previous papers. So then we went in and also tried to ask the question, okay, so let us assume we have a hairpin. Do then all these regeneration or auto-generation methods that have been proposed in the literature, do they actually work? Can we reproduce those? And there was one particular method by Su et al. That was published by the end of the last century, where the idea was that if you start with an ejection, creating one hairpin, very quickly you will get a whole succession of hairpins. So you have a primary and then secondary and so on hairpin. So parent offspring type of auto generation. So we implemented that in our code with a number of numerical tricks to keep the mean flow constant and so on. And we were actually able to reproduce the arising structures. So this is from the reference, and this is what we can then reproduce in our simulation quite well. So we could actually see for the reference case that this auto generation happens. Also this we could redo with different Reynolds numbers, different mean profiles, so boundary layers, channels, and so on. And it seemed to be a quite robust mechanism of regeneration. There was one problem though, which we realized very quickly. Oh, okay, the problem comes later. First, we can also look at statistics, and you can actually see that there's a huge growth of the shear stress due to this regeneration. So you can actually see that something happens in the boundary layer when you have this regeneration. Yeah, but there was one problem. The problem is that it was a very clean flow. It was essentially a laminar flow with a turbulent profile where this regeneration was looked at. there was one study that we found from 2008 where people tried to add some noise to the data as a kind of a model for turbulence to see how robust this auto generation actually is in the presence of turbulence. And from the figure, you could imagine that this is probably not a big problem, but it turned out it was only around 15% of the real RMS that they put in as noise. And also, it turned out it was just random numbers. It was not kind of a directed noise or dissipation that you would have in a turbulent flow. So we actually redid this experiment with noise. And since we had the DNS, so we could just take the eddy viscosity as a model and add this. And then the unfortunate result was that if you look here at the black line, that's when we had no eddy viscosity, so the kind of the laminar flow. As soon as we started to add a little bit of eddy viscosity, you can see it here of 0.02, so 2% of what the eddy viscosity should be. You can see that this auto generation actually doesn't happen anymore. So it turns out it's insensitive to the mean flow, but it's actually very sensitive to the amount of noise or modeled noise here with the eddy viscosity. And of course that kind of meant in the end that it turned out that also this regeneration mechanism is probably not what's actually going to happen. Yeah, so I guess at that point this was our conclusion that we had. We could not find any mechanism for hairpins to regenerate. We could not find them apart from regions very close to the origin or the trip. So the next question was then, okay, so we couldn't find them, but what happens if we do a simulation and we just put hairpin vortices? We know how to generate them, with this. If you have an ejection or something, then you get hairpin vortices. So we just put a lot of hairpins, and then we see how they survive and to what extent that maybe the boundary layer is modified by putting all of them. So this is what we would call a synthetic boundary layer. So yeah, that's kind of the idea. We put a lot of ejections, and we hope to kind of keep the hairpins. So it's yeah, this is just a kind of an illustration of what we expect to happen. So we put a lot of hairpins here on the left side, close to the inflow. We regenerate, and then we would get our kind of forest of hairpin. That was the idea. Now, this is not we're not the first to look at that. It was also Coles that has done similar experiments in synthetic boundary layers. In his case, the idea was not to get hairpins or to look at hairpins, but more about intermittency. But the basic idea of putting something very regular or quasi-regular and then to observe the boundary layer was something that has been done before. Yeah, so this is what happens. Again, I'm sorry that it's not extremely smooth, but the point is you put a lot of hairpins here. So these are the ones that we put artificially. What you see actually turns out that these hairpins very quickly disappear again, even though we put them and they're strong. What happens though is that you get between these trains of hairpins, you get a strong low speed streak. And if you look closely, you can essentially identify exactly what we've seen in Jane's presentation before. You see kind of this wiggle on top of the low speed streak. Of course, this is not a minimal channel, but if you think that there's a minimal channel around there. So we're kind of back into the regeneration mechanism that for turbulence that we would kind of expect. And then you get these kind of vortices on top, and these what we then would see in this region, which is really the region which has been identified as the forest of hairpins. These are essentially just the shed away vortices from the quasi-streamwise vortices doing a sinus instability rather than a varicose, as you would expect for a hairpin. Of course, this we can also look a little bit more from a statistical point of view, and we have more things in the paper if you're interested in that. So this is in an RMS plot. This is where we put the hairpins. You see they disappear very quickly, and then the strongest RMS contribution actually comes from these the secondary streaks that are being generated, which undergo a sinus instability. And then you have these shed away vortices, which is then the forest of hairpins. But there's no direct connection of what we put here to what we observe later on. Yeah, and this is kind of what where we actually stopped with looking for hairpins because we realized we could not find them, we could not find a regeneration mechanism, and even if we put them, we could not sustain them. And so our conclusion was for turbulence, for a fully turbulent flow, it would be probably very, very unlikely to actually see coherent hairpins in a boundary layer. And of course, you can now argue whether or not this is actually an important result or whether it's actually important to look for individual structures. And I guess the answer also there may be probably it's not even the right question to ask. And I went also to Ivan's paper and Jason's paper in the annual review of fluid mechanics. And in the end, it turns out also for instance, the attached eddy hypothesis or the models based on that. In the end, you don't need to have instantaneous structures. It's more about the statistics anyway. But I would just suggest to maybe not look for instantaneous hairpins anymore in turbulent boundary layers. That's maybe not the right thing to do. Okay, now I've seen that I have maybe 4 minutes left, which is good to also talk very briefly about a recent pipe flow simulation that we have performed. This is work together with Fazl's group at Texas Tech, and it was mainly G that did these simulations. So the basic idea was we realized that when looking at the available DNS data in the literature, there's of course the simulation by MK for channel flow at rate tau 5200, which with very good resolution, spectral methods, etc. But if you look at pipe flow, you see that everything stops at around rate tau 1000, 2000, maybe, far from the low order simulation by Pirozzoli from last year. So we decided maybe we should just try to go in and do a high resolution, high fidelity simulation of pipe flow as well, to have reference data also for pipe, which we can then also extensively compare to the channel data. Well, this is what we then did. It was in fact it was a longer project, maybe for the last 5-10 years, that we identified or tested different codes. In the end, it turned out that open pipe flow from Ashley Willis turned out to be a good method to actually use, because the parallelization is very efficient, and also from the discretization point of view, it really fulfilled the requirements that we had. So we set up kind of a usual set of simulations going from low to high Reynolds numbers, very much inspired by MK's kind of setup of everything. We decided then to go for a pipe with 10 pi length, just to kind of avoid any discussions about length and so on. Yeah, so it was reasonably big, not very big, but still reasonably big. We also included aspects of uncertainty quantification, just to make sure that we also have proper error bars for our temporal convergence of the statistics. We actually went with a method which is actually based on something to model the autocovariance function for our sample mean estimators, which then in the end it made it possible to also get proper error bounds for more complicated quantities, like for instance for plus scaled velocities, where you can have an error both in the mean velocity but also in the u tau. And then of course we have these very nice pictures. I'm always still amazed at how beautiful this looks like when you go from low Reynolds number to high Reynolds numbers, where you have these beautiful structures close to the wall. So this is again a representation which I just think is amazing how much you can do with simulations these days, which is in a reasonably long pipe. Now, just for the end, I have, I think, 2 slides with a little bit of statistics to give you an idea of perhaps also the quality of the data that we have. So we start with very low order statistics, just looking at the friction factor, so the pressure drop that you would get. So the Prandtl friction law, here you see it normalized, where kind of any deviation from 0 would indicate an error compared to the Prandtl law. Our data is the new data is these black squares. You have the green diamonds. These are actually other simulations that we did at the same time with our NEC 5000 code, just to validate that everything is fine. It turns out that we actually have a perfect match up to RayTau 2000, and then this RayTau 5000 is only done with one code. So this was for the friction factor. Of course, you can look at the mean velocity profiles. Here, the typical indicator function. I guess the main thing is when you look at channels, you get this beautiful plateau at a specific value of the carbon constant for the pipes. That's kind of the black line here. You actually do never converge this plateau. You're kind of always with a certain inclination, and there's a number of theories that one could have of why this is the case. RMS values, of course, they also look kind of as expected. And perhaps the most important quantity is the wall shear stress fluctuation, so tau wall RMS, where we can see that the data in principle follows everything else, like pipe channels and so on. But there is still some difference between the various pipe flow between different pipe flow simulations, which get maybe smaller at higher Reynolds numbers, but still there is some difference which is not explained simply by looking at the temporal convergence. The data, we're kind of writing up the paper now, so if anybody's interested, we can look at that. Okay, I guess I'm running out of time, so I just put up the conclusion. So we had the hairpin vortices, which was a bit difficult because we didn't find them. And then we have some of the new data for pipe flow. Okay, thank you.
I was just wondering if when you were looking for hairpins, you tried this Lutex identification. I don't know if you're familiar with this work. There's been a number of papers where they're trying to look for finite regions of rotation rather than infinitesimal rotation.
Probably not, because we did that a bit earlier, I guess. So, well, not just probably not, no. we didn't do that, but yeah.
Is that something you think would be useful, or?
I personally would now not spend time on it, because I think the likelihood of finding, you know, two nice structures is low. Yeah, so we tried what we could, and we would have been very happy to find them, because that would be kind of a major thing, but we simply didn't. So of course, I mean, one could relook at the data and see whether one would really find structures. So of course, also it's not so easy with scaling and so on. If you start to do a statistical average, you need to kind of, yeah, but.
Thanks. Another quick one. When you say you put the hairpins in the synthetic boundary layer, can you explain what you mean by put?
Well, we
did
did
nonlinear solutions, right? So
no, so yeah, so we essentially did what inspired by the Coles data. We essentially put ejections at the beginning. So we had actually a kind of a force in distributed along the spanwise direction, which kind of ejected at certain time instances. So you would create a streak, which then very quickly gives, because it's time dependent, it would give you this roll up of the hairpin. In the Coles experiments, it was little pistons that went up and down to essentially do the same.
So I've got maybe a naive question. So you're saying that the hairpins aren't really seen in these flows persistently. So what should we think about in terms of like an attached eddy model? What should the attached eddies look like? Because classically they look like hairpins.
Well, that's maybe.
I don't have any skin in this game, so.
Well, I don't know. That's maybe that's a difficult question for me to answer. I think, I mean, the fact that you need to have something that scales with the wall distance that you can then simplify into a certain shape. I think this is clearly the case. But I guess also, as Ivan points out, or maybe which you can confirm, is that it's the actual the shape is maybe less important than you have the correct scaling.
Philip, thanks again for a nice talk. And we tried some 25 years ago or so to look for the head part of the hairpin experimentally in a reasonably high Reynolds number boundary. In those days, it was not as high as we can do now. And we tried both with conditional hot wire data. That's in work paper in JFM, I think you're familiar with it. And we found the legs, but not the arch. And we, with visualization, that's unpublished work, but I have many videos one can watch. We could never find the connected arc.
No. And I guess that's very consistent to what we've seen here. Yes.
Okay, thank you. I mean, there is one last question by me. I mean, are you familiar with the second paper by Bo and Moyne, where they claim that there are these hairpin carpets very near the wall that happen only locally?
Yeah.
I assume under sweeps or something like that.
Yeah, that's was 2013 or so.
Yeah, something like that.
Yeah.
I mean, that Reynolds number is high, but they only happen locally. I mean, they're not everywhere.
Yes, but still, it would. I would still think that you would find it with one of those with one of those induction methods.
But they're small. I mean, the things are small. Are always near the wall.
Yeah, exactly. But in particular, the method by Beijing was also close to the wall. I mean, you try to connect it directly to the walls.
Over everything. And
yeah, I mean, we try to actually look at the structures also, not just blindly doing the average. We could never find anything. I mean, even if you follow the leg and you, I mean, yeah.
Okay, so thank you again.